All right, let's dive into a paradox that, believe it or not, powers our world. How in the world do you start a massive motor without basically causing a blackout? Well, the answer seems to fly in the face of basic physics, but it's a clever trick engineers use every single day.
So here's the head scratcher. We're all taught that for a constant power device, if you lower the voltage, the current has to go up. It's just math. Think of a garden hose. If you squeeze it, the pressure, kind of like voltage, drops. But the water has to flow faster, right? The current increases. And yet, to start these huge motors, engineers do the exact opposite. They drop the voltage on purpose to reduce a massive surge of current. So what gives? How does that make any sense?
Well, the secret is that we're not actually dealing with just one machine here. An AC induction motor kind of has a split personality. It acts one way when it's just starting up from a dead stop, and a completely different way once it's up and spinning at full speed.
And this right here, this is the single most important idea to solving this puzzle. You have to stop thinking about it as one thing. To get this, you have to see it as two totally different devices packed into the same metal body. The motor at rest and the motor in motion.
So let's break down these two identities side by side. On the left, at startup, what they call a locked rotor, the motor is electrically simple. I mean, really simple. It's basically a chunk of wire. Lower the voltage, the current drops. That's it. All it's trying to do is get moving. But then, look at the right. Once it's running, it transforms. It becomes that constant power device we talked about, and the rules completely flip. Now, to maintain its power, if the voltage goes down, the current has to go up. Two states, two totally different sets of physical laws at play.
So how do we wrap our heads around that initial startup phase? Well, someone came up with a fantastic analogy that just makes it all click.
A Reddit user, V8-64, absolutely nailed it. For that split second when a motor is starting, it's not really a motor yet. It's acting just like a transformer with a short circuit. All that complex stuff with spinning fields and forces, that's not happening yet. It's just raw, simple electromagnetism.
And when it's in that shorted transformer state, the rules are dead simple. It's just Ohm's law, plain and simple. You lower the voltage, you lower the current, end of story. And that's the whole magic trick the star delta starter is pulling off.
Okay, but that only explains the first few seconds, right? So what happens next? How does the motor morph from that simple circuit into this powerful spinning machine? Well, to get that, we need to look at the physics of how it actually runs.
It all kicks off with something that's, well, kind of beautiful from a physics standpoint. The three-phase power supply creates this invisible magnetic field inside the stationary part of the motor, that's the stator. And this field is constantly, smoothly rotating. It's like a ghost, a spinning force that makes everything else happen. Now, this magnetic field doesn't just spin at any old speed. It spins at a very precise, constant speed called the synchronous speed. And that speed is locked in by two things: the frequency of your power grid, 50 or 60 hertz, and the physical way the motor is built. And here's where things get really, really clever. The spinning part of the motor, the rotor, is always chasing that magnetic field, but it's designed to never quite catch it. There's always a slight difference in speed, and that difference is called slip. And slip isn't a problem. It's the whole point. Without it, the motor wouldn't do anything at all. Think of it like this. Because the rotor is falling just a little bit behind, that powerful rotating magnetic field is constantly sweeping across the metal bars in the rotor. That motion induces a current in the rotor, which in turn creates its own magnetic field. So now you have two magnetic fields, one in the stator and a new one in the rotor, and they're pushing and pulling on each other. That push and pull, that's torque. That's what makes the motor spin. So no slip means no induced current, and no induced current means zero torque. It's that simple.
Okay, so now that we get the motor's two personalities, the simple circuit at the beginning and the complex spinning machine when it's running, we can finally see the absolute genius of the star delta starter. It's this really elegant two-step dance. First, you start the motor with its windings connected in a star shape. This is the clever part. It automatically reduces the voltage to each winding, giving the motor that gentle, low-current start we need. It's in its simple circuit mode. Then, after a few seconds, once it's spinning, a switch flips it over to a delta configuration. And that unleashes the full-line voltage, transforming the motor into its high-power, high-performance running state. It's a gentle ramp-up instead of a violent jolt.
And the difference this makes? It's huge. Just look at these numbers. If you just switch the motor on directly, it could draw a staggering 590 amps. That's enough to dim the lights for the whole block. But with the star delta start, that initial surge is slashed to a much more manageable 340 amps. The whole electrical system breathes a sigh of relief. But you know how it is in engineering. There's no such thing as a free lunch. There's always a trade-off. By cutting that current, you also have to give up a massive amount of starting torque, that initial twisting force. We go from a really strong 310 foot-pounds all the way down to just 103. That's a 2/3 drop.
And that's the heart of the matter, really. It's a deliberate compromise. You're giving up some brute strength at the very beginning in exchange for a smooth, gentle start that won't stress out the whole power grid. This is why you see it on things like big fans or pumps, things that don't need a massive kick to get going. So, let's bring it all home. What's the one big takeaway from all this? What's the final answer to that paradox we started with?
The paradox it evaporates. It disappears the second you realize you're not dealing with one machine, you're dealing with two. At startup, it's a simple circuit where less voltage absolutely means less current. But once it's up to speed, it transforms into a complex machine where the rules flip. The star-delta starter is just the ingenious device that manages that transformation, giving the motor exactly what it needs at exactly the right time.
And this dual nature isn't just a fun fact for a pub quiz. It's a fundamental principle behind the heavy machinery that runs our modern world. It's just a fantastic reminder that sometimes the most confusing problems have incredibly elegant solutions hiding right there in plain sight. Makes you wonder, doesn't it? What other everyday tech has a hidden secret personality we don't even know about?